we present CAGE, Controllable Articulation Generation. Articulated objects are ubiquitous in real-world scenes. Digital 3D models of these objects are useful for various tasks in robotics, 3D vision, and embodied AI systems. Unfortunately, 3D models of articulated objects are predominantly authored manually, limiting scale and diversity of objects. There is recent work on reconstructing articulated objects from real-world observations. However, these methods either rely on laborious acquisition of real-world data or assume the existence of large 3D datasets to enable articulation. These assumptions limit the scalability of these approaches. The recent proposed NAP is a generative model that generates an articulated object from random noises. Although NAP conceptually supports conditional generation given partially specified inputs, it often fails to respect input constraints, limiting controllability for users. This limitation clearly contrasts with users' natural desire for control over the generation, especially for highly structured and compositional output, as is the case with the articulated objects. In this work, we tackle the challenge of generating 3D articulated objects with fine-grained controllability. We take a directed graph specifying the part connectivity and an object category label as input conditions. With our method, we generate the bounding primitives and articulation for each part in the graph. We then retrieve part geometry to compose a complete 3D articulated object. Our work relies on three key ideas. First, we leverage the interplay between part shape, connectivity, and motion using a diffusion model with attention modules to extract the correlations between part attributes. Second, we lift part geometry to a shape abstraction to effectively capture shape-motion correlations. Lastly, we leverage key actionable parts like door handles and their relationships to other parts to provide a strong signal about likely motion patterns. In this example, the handle on the left top corner indicates the door is more likely to be opened from the left rather than from the right. Together, these ideas enable fine-grained generation and control. Concretely, our method represents each object as a collection of part attributes X. In a forward pass, we follow the usual diffusion process by adding Gaussian noise iteratively to corrupt the data to randomness. During the reverse process, our denoiser predicts residual noise to be subtracted from the input data at time step t, conditioned on the category label C. Our denoiser is built on layers of attributes attention blocks, which stacks 3 attention modules in between. Here we show the details of our attention modules. Each node in the input graph is represented by 5 attributes describing part shape and motion parameters. Each attribute is a separate token to be attended. We designed 3 attention modules with varied masking strategies. Here, the gray cells indicates the attention that has been masked out. Local attention captures the relationship of attributes within the part itself. The mask only activates attention among attributes within the same node. Global attention captures relationships among nodes regardless of topological distance in the graph. This allows for attention between pairs of attributes across all valid nodes. The graph relation attention focuses on the relationship between attributes among parent and children nodes. Here we leverage the graph structure as a condition by explicitly masking the attention using the graph adjacency matrix. Here we show qualitative examples of generated objects conditioned on graphs of varied complexity. The generated objects respect the node hierarchy with parts better matching the input graph, as denoted by the color. In comparison, prior work fails to conform to the input graph with inconsistent part assignments and flipped or disordered connections between parts, denoted using red arrows. Our method can be conditioned on graphs that are out of the distribution of the training samples. These results illustrate that our methods can generate plausible objects even for unseen graphs with different numbers and compositions of parts. Our method can also be conditioned on specific attributes associated with the graph. Here we predict part articulation parameters given a bounding box condition for each part. The output plausibly completes the object given the provided input parts. Here we condition on specific part articulation types in input graph. The output objects demonstrate various possible completion for the given joint type, each compatible with the specified input condition. We can also condition on a specific articulation axis for each part, as shown here. The generated variations again demonstrate plausible objects that are compatible with the input articulation axis. Please refer to our paper for quantitative evaluation results and more details. Thank you for watching.